Bismillahirrahmanirrahim. Welcome to this session. Before starting this session, if you have any question from the last class or any part of your syllabus.
No questions here.
Yeah. No question. Okay. After this lecture, we have another lecture tomorrow. Inshallah, by tomorrow we can finish our lecture we can finish our syllabus for the final term. I have decided that your exam will be an open book exam, so you can use any sort of sources, whatever you like. So you can take your preparation accordingly. You do not need to memorize the things, so you can use all the documents, necessary documents for the exam. Okay, so it is necessary to build your concept for the exam and also for your future. Okay, so in the next day, if we can talk about the exam process and other things if necessary, inshallah. And today we'll try to end up the discrete Fourier transform. In the next day, we'll talk about the first Fourier transform. Okay, so we were discussing about this circular shifting, and I have thrown this question. So why this circular shifting and how this circular shifting is equivalent to the linear shifting? Why this is important to understand? Try to understand this portion. Conventionally, what we have done in case of linear shifting, let's say we have these 3 samples, and this is your xn. Whenever you want to shift one sample, that means xn minus 1, the output looks like they are shifting one sample to the right. So pretty simple. So it is shifted one sample to the right. This is 0, 1, 2. This is 0, 1, 2, 3. Now, according to the definition of the discrete Fourier transform, our range of vision, let's say our range of vision is from 0 to 2. So let me take the things to the right place. Just a minute. So 0 to 2 is our range of view. So now if we shift to the right, then what happens? This was our range of view. So we are out of the range of view, and that makes a problem. And that's why it is converted to the circular shifting. What does it mean by the circular shifting? As we have already mentioned in the last class. So these 2 samples are shifting to the right, okay, no problem. And this sample should be shifting to the front place. So the sample, the x n minus 1 is now looks like this. So this is a 0 sample, first sample, second sample. Now the question is a very important question. How we can say that the frequency domain response of this x minus 1 of the linear shifting is equivalent to the circular shifting of xn minus 1, where we should write in this way xn minus 1, and the subscript there should be 3, where the capital N is equals to 3. So by this time you know that what is capital N. So the question I'm repeating again, in case of linear shifting, we have already mentioned this. So xn minus 1, and it looks like this. Completely, it looks like this. Now the question is, apart uh, by the linear, the circular shifting, now it looks like this. Now the question is how we can say that this circular shifting, the circular shifting doesn't make any impact to the shifting operation comparing to the linear shifting. That is the question, fundamental question. Okay, so before describing those facts, we have already mentioned that if we start with the xn, where we have 0, 1, 2, 3, so 4 samples. So capital N is equals to 4. For this case, if we do the Fourier transform, we have found discrete Fourier transform. We have found xk, which is of course a periodic function. We have already learned that. And whenever we have done the inverse discrete Fourier transform, we got back our xn. However, this is also a periodic function at this moment. So according to that, we can write that this is our xn and this is our periodic xn. So this is the new xn we have found. And now whenever we are looking at linear shifting of this, for example, we are doing xn minus 1, what happens? Try to understand here. We are shifting all the samples to the right. And of course, this 0th sample came here, the first sample, second sample, this third sample. And unfortunately, this sample goes out of the range because our range of view is from 0 to third sample. So this sample is out of the range. On the other hand, if you consider this sample, of course, that belongs to the 0th sample. Now the sample output looks like this. This is 0, this is 1, 2, and 3. So the 0th sample looks a higher value, then lower value, little bit higher value, and this is the value. So this is the portion of xn minus 1 due to the circular shifting. To understand the circular shifting, we always put this subscript of the n value. Okay, so this is all about the circular shifting. Why logically it should be looks like this, how it can be. Now if you are shifting more, definitely in that case this sample will be shifted to the 0th sample, and this sample will come here, and this sample should come here, and these are the 4th sample, they will, and these samples, all other samples will remain the same. So we have mentioned in the earlier section that if this is x0, x1, x2, x3, for example, so they will be shifting like this. Okay, so that is the concept of the circular shifting. Now the question again, how this circular shifting, this is the end product of the circular shifting for our case. This is the end product of the circular shifting for a single time shifting. So now we need to understand, if it is a practically shifting to the right, what happens? If it is practically shifting to the right. Now you need to understand that our basic signal, we start with this. However, our basic signal now looks like this. Try to understand this analogy. If we have, let's say, if we have a, this is an analogy, so try to keep it like that. If we have a sinusoidal signal, this is periodic or aperiodic. Of course, this is aperiodic because you do not have anything after that and before that. So this is your xn. Whenever you have done the Fourier transform, discrete Fourier transform, and then do the inverse discrete Fourier transform, this signal, this is in the continuous time. Just think about this is in the discrete domain, so it will help us. In that case, what happens? It will give us the periodicity of the output. So now it looks like this. So this is our xn. This is xn, and that will definitely repeat, and it will repeat forever. Okay, you can extend it. Similarly, in the first section, that will repeat, and this will repeat like this. So you can understand the process. This is what, this is our xn period. Okay, now the question is, if we do the Fourier transform of this part, of course, what we can find, whatever the amplitude and the phase, whatever the case, amplitude and the phase, since this is a xn, a sinusoidal signal, a single frequency will be there. So single frequency will contain the signal. So of course, in the output, you should find a single stem, isn't it? So let's say this is your omega. I should write in this way. Yeah, omega equals to 0, and let's say this is omega is equals to pi. Okay, so in between we are getting a single stem due to this Fourier transform, discrete Fourier transform. Similarly, what we can understand for this case, that means the periodic of xn, what you are expecting in the frequency domain, the omega equals to 0 and omega equals to pi. You are basically dealing with the same frequency component, so they are dealing with the same frequency component. So that's why you should get the same kind of stem, let's say omega equals to omega 1, at the same location. There is no question about that. Okay. Now, for shifting operation of this kind of scenario, when we are shifting this sequence, let me draw it in the black lines. So how it looks like, I'm shifting it to the right. Okay, so approximately it should looks like this. And after shifting that, so again, I'm telling that this is a continuous signal. Just let that it can be discretized, and then we have xn. So now after shifting, that is xn minus 1. Let's say that, do that. And now if you do the Fourier transform of xn minus 1, what happens to the magnitude response? Do you have any change in the frequency domain? Magnitude response for the black line? Any of you?
No, sir.
No changes. So that means it will be at the same location because the frequency hasn't been changed here. So that is very, very simple to understand. Okay. So we have found that due to the shifting operation, only the phase will be changes, of course. However, the magnitude response remains the same. So try to understand it with the magnitude response. Now, what happens? You can see here, if we concentrate on a particular time segment. So let me choose the time segment for this. So this is our time segment. According to the DFT, this is our time segment. So we should look into only to this segment. So where is that segment? So this is that segment. This is that segment. And if you consider the black one, the shifted one, how you can find it? So it starts here, and you can see that it is shifted to the right. So this is the whole segment. Basically, we have this segment only. So it is nothing but the shifted version of the purely sinusoidal signal. Now, if I take the eraser and erase this black one, so I'm erasing the black one. Okay. Basically, we are considering only this part, this one, this orange part. We are taking that. So after shifting this one. So if you are doing that black line and the Fourier transform of that one, apart from that, if you do the Fourier transform of this one, it gives the same thing. It gives the same thing. If you can consider this portion, this tail basically came from this front portion. So this actually came to the back. You can understand. So this tail, this front part basically comes to the back part, and it means the same thing. If you process the whole Fourier transform process, it will give you the same result. Okay, so if we consider the black one, just the black one, so we can find that in between this we have the full cycle. We have the full cycle. As before, we have the full cycle. We start with that full cycle. We got the full cycle again, but that is now a shifted one. Since we have the full cycle here, this red one, now this red one, we have the full cycle. We should have the same stem at that location. That means at that location, but it should be now shifted. Because whenever you are, we know the basic of the Fourier transform. What we are doing the correlations of the different signal. Of course, previously, whenever it was like this, then pure sinusoidal signal, pure sine signal actually been correlated. So it shows the phase 0. However, when it has been shifted, when it has been shifted, now it looks like this. So we should take it up to this. So we are taking up to this, from this to this. So that is our range of view. This is our range of view. So now if you consider this, so in between what we have the signal like this, which is also alike of the sinusoidal signal, but that is a shifted version. So that gives us the shifting as well. That will also give us the essence of the shifting. So what we can understand here very clearly, that this orange mark, so look at this one, this portion basically comes to this portion for a repeated function, So from that same logic, we can say that whenever we have this signal, it has been shifted, means that the the front side can become to the tail side, and that makes sense from the repeating function of the time domain sequences. So if we can say again, for this one, if we have the magnitude response looks like this, of course for that one we have the same magnitude response, and for the shifted version we have the same magnitude response. However, the phase response will be changed accordingly. Okay, so logically we can understand that the circular shifting and the linear shifting basically works like the same. There is no problem with that. Okay, so we have already mentioned these points as how the circular shifting been compared with the linear shifting. Okay, so we were talking about the properties. Another property is the time shifting. We'll talk about the circular shifting with some example again. Time shifting in the time domain will give the phase shifting in the frequency domain. That exactly like the Fourier transform. So whatever we have learned there, frequency shifting in the time domain, of course, it will shift in the frequency shifting in the frequency domain. Convolution, circular convolution. So now before we have doing the linear convolution, now we are defining the circular convolution. Whenever we are writing the circular convolution, we need to write like this. We need to subscript the value of the n. So circular convolution in the time domain gives the multiplications in the frequency domain. Now, to be very specific of the circular convolution, what are the we will give some example with the particular values. Okay, for the linear convolution, we have our sample, and we are putting this kind of symbol, star symbol, and then the other sample. And mathematically, this is the algorithm. So we have our input, and we have the impulse response and the shifted version of the impulse response. You know what are the process. First, we need to do the folding operation and the shifting operation. And it is also true that we can do it vice versa. M equals to 0 to n minus 1. We can put h m and the g n minus m. That is also true. We have also learned it. So I have given a much higher time for understanding the linear convolution whenever we have covered that. Okay, now about the circular convolution, by the symbol we should express it like this: gn and n with a circle. It shows that this is a circular convolution, and everything looks like the same, where the difference is we need to define the value. Capital N should be defined here, and we need to put this capital N over there as a subscript. Okay, now we can give one example. Example for Gn is given like this, and Hn should be given like that. Sometimes you may ask me that, is that all the signal should start from the 0th sample? The answer is yes. Sometimes it might happen that, let's say, the Hn could be looks like the 0, 0, 2, 2. It might happen. Still, we need to put that, okay, this is the 0th sample. So we always start with the 0th sample. As we have mentioned that for n start with the 0 to n minus 1. Similarly, sorry, this not n, this small n. The capital N also from 0 to capital N minus 1. So always it start with the 0th sample, whatever the value we are getting there. Whatever the signal you have. Let's say you have some signal like this. What is the starting value? The starting value, of course, there is no starting value. That means they are the zero values. So then we have the stem here, we have the stem, we have the stem, we have the stem, something like that. So what is our sequence? Our sequence is from this to this. This is our whole sequence. And you are dividing the number of samples like this. So if I can make you clear the idea, this sample is the 0 value. They have the some value. They have some value. And the last value is also carrying the 0. So no matter whatever the first sample and the last sample, but it must start with the 0th sample, then first sample, second sample, third sample, and so on. Okay. Now we need to do the circular shifting. So this is our equation. First of all, we are just doing step by step. So this is our Gn and this is our Hn. So what is the first operation? The first operation, we can write the equation in the left so that we can understand it. This is from n equals to 0 to capital N minus 1. So capital N is equals to 4. 4 minus 1 is equals to 3. Then G M and H N minus M. So we have this equation. And of course, we need to put this capital N over there. And what we are looking for the circular convoluted output of this one. So that is our target. So what we can understand very clearly for n equals to 0, that is the first one. So YC0, we need to find out. For that one, this should be 0. And it looks like H0 minus M. So H minus M. H minus M means what? That is the H minus M, or that is the folded version. That is a folded version of the Hn. It's a folded version. So how we can get the folded version of that one? So this is bit important to understand how we can do the folding operation. Logically, what we can find here, let's say for sample, this is x0, this is x1, x2, and x3. If we do the folding operation means it looks like a mirror operation. So the folding operation gives this. Try to be with me. This will remain at the same place because it's a mirror effect. And this x1 should goes to the opposite direction to that place, and x3 should moves to that place. So the output looks like this. This should be x0 and this is x2. This should be what? x3 and this is x1. That is the folding operation from the circular shifting point of view. Okay, and it has been shown here. If you can follow that, this is x0, this is your x0, this is x1, this is x2, this is x3. So x0 will remain at their same place. So straightforward, this will remain there. What about x1? It should be goes to the place of x3. So that's why it shifted to this. And what about x3? x3 should be shifted to the place of x1. And what about x2? That should be remain at their own place. So this should be remain at their own place. And this is the result of what? This is the result of H minus M. That is the result of this. This is folding operation in the circular shifting. Folding operation in the circular shifting. Okay. So I believe the idea is clear. Now, if we want to, okay, so let me give another example of this notion, how we can understand this from the linear shifting as well. So in the linear shifting case, let's think that we have these 3 samples. Okay, let me give 4 samples. Okay, so this is 0, 1, 2, 3. And this is your Hn. If you want to find H minus N, what will happen? It gives the value. This is 0th sample. This is -1 sample. -2 sample, -3 sample. So it will be 0, -1, -2, -3. This is very simple. Now the question is how it can be related to the circular shifting, because according to the circular shifting, what we have found, just now, what will be the result? The x0 will remain stand still. Let me draw it here again, just to understand the process clear. 1, 2, 3. Okay. So this is your HN again, and this is what we are trying to draw here. This is according to the circular shifting, like 4. Okay, according to the circular shifting, what will be the result? So this will remain at the same place. Okay, so I'm putting the places first. Okay, this is x0, this is x1, this is x2, and this is x3 as well. This is x0, x1, x2, and x3. As we have already shown earlier, that this x1 will goes to the x3 place of x3. So it should be looks like this, and the x3 comes to the x1, the highest value, this, and the x2 remain at their original place, like that. So the swapping is that x0 will come to the x0, x2 come to the x2, x3 moves to the x1, and x1 moves to the x3. What we have found in the earlier lecture. Okay, so now this is your circular shifting. This is your circular shifting version. But now you can compare with this to that. This is a linear shifting version, and this is a circular shifting version. Okay, as we have already know that this xn, this is in our time domain, it has been repeated in case of discrete Fourier transform. So what happens? It actually looks like this. Practically, it looks like this. I'm not repeating more, so you can understand. It should be looks like this. So it will repeat. It will repeat. So whenever it will repeat, whenever we are doing the folding operation of that, what happens? You are getting this output like this, and 0, and so on and so on. And now you can consider this is 0, this is 1, this is 2, this is 3. This is what? This is for the linear operation, just folding operation. And this is for the circular shifting folding operation. And now if you consider this portion from the 0 to 3, this one, this is exactly the same of this one. So they actually give you the same result. So whenever you are doing the folding operation, in case of a repeated function, it is equivalent to the folding operation in the circular shifting, what we have shown. So from this example, we can understand that this process actually been valid. After doing that, then the second one is, if we are talking about 1 minus m, so that means for YC1, position number 1, what happens? This will be shifted right. So 2 goes there, 1 will be there, 1 will be there, and this will come to the first place. So similarly, for 2 minus m, Don't be confused with the value of m and n. You can this is for a particular example. You can always because m and n both are dummy constant. You can use it with m value or n value. Just try to understand the process. So for other shifting, again one more shifting, and this will come to the first place. Another shifting. So how many shifting we need? We need 4 shifting operation. This has been discussed here. For n equals to 0, we have h n minus 0, and this is 1. For n equals to 1, this is 0. And for n equals to 2, that is h n minus 2. Whenever we have minus, I have already mentioned that you can replace it by h4 minus 1, 4 representing the value of capital N, and that gives you the value of h0. What I have mentioned here, whenever we are talking about the h minus n, this is for n equals to 0. This is the folded version of that. So how you can find those value? How you can find this value? Let put that for the 0th sequence of m. We have put it that this is m is equals to 0, so 0. So this is equals to h0. If we go for h1 first location, this is equals to minus 1. You should write 4 minus 1, that is equals to h3. Similarly, h minus 2, this is equals to h4 minus 2, that is h2. And if we move for h minus 3, that is h4 minus 3, that is equals to h1, which we have already mentioned in the earlier section. That means 0th sample and the second sample remain at the same place, but the third sample and the first sample, they actually been swapped between each other. So you can find any value with that logic. So in the equation, what we can found here, this is our basic equation. Okay, so pardon me, there should be capital N to make we understand this is our circular convolution. So the detailed calculation has been given here for n equals to 0. For n equals to 0, this is the equation. Now put the value of m for each and every point, and then we can find that. Okay, I'm just considering z0, it has been given. h0, it has been given. g1 given. h minus 1, no, it is not given, because h is given like this. Okay, let's say we have some value which actually start with the 0th sample. There is no negative sample. Whenever we have the negative sample, this should be replaced by h4 minus 1, which is equals to h3. So what is the h3 value? This is first, second, and third. So that value should be replaced to that place. Okay. So similarly to this one and this one, I have already shown it. And you have got those numbers, and ultimately you can find out this YC0. YC0 means this is the output YCN. What is the value at the 0th sample? We got that is 6. So this is 6. Okay. Okay. Similarly, you can do the process for YC1, YC2, YC3, and you will get this value, this value, this value, this value. And so this is the circular convolution. We have done the circular convolution like this. Now the question is, how can you perform the linear convolution with this circular convolution concept? If we take the example like this, let's say in case of a linear convolution, if we want to perform the linear convolution, what happens? Let's say Gn, how many samples we have? We have, let's say I'm just giving some number 2, 2, 1, 5, okay? And the Hn is equals to 1, 2, 1, 3. If you do the linear convolution, let's say it start with 0 and it start with 0. If you want to do what? The linear convolution with the help of circular convolution, that is our target. So the linear convolution, we know that the linear convolution can be defined as the n equals to 0 to n minus 1, then g, this should be m minus 1, gm and hn minus m. If that is so, this is for the linear convolution. We have 0 to 3 and we have 0 to 3. So if you can remember, how many samples you should find in the output in the linear convolution? How many samples? The lowest value of the sample should be 0 plus 0, which is 0. And the highest number of the sample should be 3 plus 3, which is 6. So how many samples you are getting out of these two inputs in case of linear convolution? What is the output sample size? The output sample size should be 0 to 6. 0 to 6. So you have 0th sample, 1, 2, 3, 4, 5, and 6. You have 6 samples. Now the question is, you need to find those values. So I'm talking about, you need to find y1, sorry, 0, y1, y2, y3, and up to y6. You need to find that. So how we can do that? By using the circular convolution. The step number 1, what we need to do, the output size, before going there, if we do the circular convolution between Gn and Hn, what would be the output size? Any of you? If we do the linear circular convolution between Gn and Hn, what is the output of the circular convolution? What is the sample size? How many samples you should find in case of circular convolution? What should be the output size? You are not in the lecture, isn't it? In case of circular convolution, how many samples you should find in the output? You should get 4 samples, isn't it? You should get 4 samples, the same number of samples you should find. So if you want to find 7 samples in the output, what we need to do, we need to pad these 2 inputs with zeros. So that means we have 0, 1, 2, 3, 4, 5, 6. We need to pad more 3 zeros. Similarly, we need to pad more 3 zeros like this. Then we got our signal ready to do the circular convolution. Now, whenever you are doing the circular convolution, how many samples you are now looking for? You are looking for 0 to 6 samples, so total 7 samples. So this is your task. With this example, this is the inputs. Take this Gn and Hn as your input. If these are the inputs, do the linear convolution by using the circular convolution. Do the linear convolution by using the circular convolution. Okay, at the end, we'll show you why this is necessary, why this circular convolution actually help us in place of a linear convolution. Okay. But I have mentioned that the process how to do the circular convolution, the linear convolution using the circular convolution. Okay. Now there is another process. This is the previous one is based on the equation. We can perform this circular convolution. Now the second term is by using the Fourier transform. As we already know that the circular convolution, it can be mentioned like this: Hn in the time domain is equivalent to the multiplication in the frequency domain. So what is the strategy? First of all, we'll convert our Gn to Gk and Hn to Hk by using the discrete Fourier transform. And after that, we can multiply those two. And after that, what we are doing inverse discrete Fourier transform to find the output Yn, which is nothing but the circular convoluted value or the output. Okay, so that is the process we'll follow. So I believe that you can understand very easily because that is the algorithm. So this is Gn is converted to the Gk. So no need to explain the things. You will understand the things whenever I will share this PDF. And this is the equation, elaborated equation. And now put the value for k is equals to 0. This is the 0th value, first value, second value, and third value. By putting this, replacing this k value is equals to 0, 1, 2, and 3. So we have found the Gk looks like this. And you have found the Hk looks like this. Okay. Okay. Right. And then we need to multiply them. So this multiplication is point-to-point multiplication. If you can follow, 4 multiplied with 6, 24. 1 minus j, 1 and 1 minus j, it gives this value. Minus 2 and 0 gives 0. 1 plus j, 1 plus j, it is twice j. Okay. We have these values. And this is the last portion. Here, what we need to do, we need to do the inverse discrete Fourier transform of our product. We have already found this. And do that inverse discrete Fourier transform for a different value of n, and you will get this result. This can be also asked in the viva or in your final exam, that show that the circular convolution can be done. Circular convolution, you can write this question. Circular convolution can be done by using discrete Fourier transform. What would be the proof? What you need to do, you need to find YCN by using Gn linear the circular convolution in the time domain, as well as you need to find it with the discrete Fourier transform, where we have already mentioned that Gn converted to Gk, Hn converted to Hk, and after that Gk and Hk should be multiplied, and then inverse discrete Fourier transform will give us YCN. So you need to find YCN in this process, you need to find the YCN in this process, and then you need to show that, okay, yes, they are like the same. So the circular convolution can be done by using the DFT. Okay. The next process I'm not discussing here. If you want to go through, you can go through that topic, but this is not very important to understand at this moment. So we have actually done the things like this. So we have already discussed in some part previously, so no need to explain here at this moment. So as I have already mentioned that, what is the advantage of knowing this process by using DFT, doing the circular convolution? What is the advantage of that? As we have already know that whenever we are doing the linear convolution, as we know that we have Gn and Hn minus n, m, and m is from 0 to n minus 1. We need so many multiplications and addition here. However, whenever we are doing the Fourier transform, we can say that it is less mathematically, mathematical consumption is lesser than the time domain calculation. How that is so? Because whenever we look at this, let's say we have our Gn, we convert it to Gk. What we are doing there? We are doing some matrix multiplication like this, where we have a matrix D4, which is nothing but this kind of value. Because as you know that what we are doing, we are giving our Gn, and then Wn is the multiplication value to the power Wn to the power Kn. So based on the position, this value can be already found, and this matrix can be built. This matrix can be built. And as you can understand this matrix for a particular value of capital N, let's say the capital N is equals to 4, this looks like this. So this is a constant value. What I have mentioned, if we can go back to this is our equation. For n equals to 0, for n equals to 0 to 3, we have that equation, and for a different value of k, we have the equation. So how many equations we have? We have 4 by 4 matrix of this. We have different value of Gn. Of course, this is independent, but this is, of course, a constant value. What does it mean? We have, let's say, for k is equals to 0, we have Wn to the power 0, where n is equals to n into 0. And for k is equals to 1, we have Wn to the power n into 1. So how many values we have there? For this one, we have 4 values. For n is equals to 0, so we can write 0 into 0, Wn 1 into 0, and so on. So we can write in this way: Wn 0 into 0, Wn 1 into 0, Wn 2 into 0, and Wn 3 into 0. So first one is for n, and second one is for k. Similarly, we can write Wn, n is equals to now 1, and k is equals to 1. Wn, n is equals to 2. Sorry, I made mistake. N is equals to 0 and k is equals to, in this way, this is k equals to 0. This is, okay, yeah. This is 1 and k is equals to 0. Wn, this is n is equals to 1 and k is equals to 0. N is increasing, should be 0 here, n, and k should be 1. K should be 1. The first one. Just a minute. We are putting k equals to 0. All the zeros are there. Now k is equals to 1. Wn, k is equals to 1. Wn, k is equals to 1. What about n? N is also increasing. N is increasing. So the n is equals to, let me check. N is equals to 1, n is equals to the 1. Oh, this is 0, sorry, 1, this is 2, and this is 3. Yeah, now this is okay. And another one, wn, 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 wn. This is n is increasing in this section. The k is increasing in this section. So this is 0, 1, 2, and 3. This is for n, and for the k, this is 2. This is 2. This is 2, and this is 2. And the last value 0, n1, wn is 2, and wn is 3. And what about k? This is 3, this is 3, this is 3, and this is 3. So what I am mentioning here, we have found this matrix. We have found this matrix, and this is equals to your D4, where everything is known to us. If everything is known to us and that equation looks like this, so that means we always find this value. So if you already calculate this, then you can save it already whenever you know that n is equals to 4, already you have this database. Okay, so whenever you are doing this calculation, this is less mathematically consuming time consuming concept. So that's why it will be very fast, because it has been already known by the computer. They can make the computation very fast, and then it will be multiplied with that. Okay, so the process, the matrix multiplication. And similar to that, as you can understand that you do not need to calculate this again. However, in case of the linear convolution, whenever we are doing the linear convolution of Gn and Hn, everything should be calculated individually. There is nothing known there. Okay, here we have a bigger part which is known to us, and after doing the calculation, this is the process, the inverse. If we want to do the inverse processing directly, we can done this process where D4 star, it also been known, D4 star mean the conjugate, the complex conjugate of the D4. So what is the value of that one? If we have this one, just these complex values sign should be changed. Whenever we have plus sign, that should be converted to the minus sign. All other values should be remain the same. So in a sense, if you know the D4, the D4 star is also known to the computer, then do not need multiplication and other things. This is called lookup table process. So by lookup table process, you know this, and you have already calculated this and this with a very simple calculation. Now you can find your output in the circular convolution. And that is why I am telling that the Gn and Hn, if you want to do the linear convolution between these two, the first thing what you need to do, you need to pad with zeros by targeting what is the output. What is the output? As I have already mentioned, if you have 0 to 3 sample, you need the output from 0 to 6 sample. So you need to pad it with 0, more 3, more 3. And after that, what you need to follow? You need to follow the process. Gn should be Gk, Hn should be Hk, and then multiply them and doing the inverse Fourier transform in the frequency domain. So that gives the final output. So this is the process how you can do the linear convolution as well by using the discrete Fourier transform. And whenever you are using the computer, of course, people are using this process for the convolution. Okay. Okay, so that is the last topic of from the discrete Fourier transform. That is all about discrete Fourier transform. In the next day, we'll talk about the first Fourier transform, the mathematical concept. Basically, this first Fourier transform is nothing but a mathematical concept, or you can say one kind of algorithm that makes our Fourier transform, or you can say discrete Fourier transform, more faster. That's why this is called first Fourier transform. That is not a particular algorithm. There are a number of algorithms which has been those uh, those are using for making the discrete Fourier transform more faster. Altogether, everything knows as the first Fourier transform. So in the next class, we'll talk about this. Okay, at this moment, if you have any question from today's lecture. Okay, it sounds that you don't have any question. Okay, thank you for your participation.